is Kyle Pelphrey, and in this presentation I will be showing how to work this combined spectral problem for the molecule C7H14O2. We will do this by using infrared spectroscopy, carbon-13 nuclear magnetic resonance, and proton nuclear magnetic resonance. So, to begin, we must figure out the degrees of unsaturation for this molecule. To do this, we will use the following formula. So the degrees of unsaturation is 2 times the number of carbons plus 2 plus the number of nitrogen atoms, which there are none in this case, minus the number of hydrogen atoms minus the number of halogen atoms, which there aren't any halogen in this case. The number of carbons, 2x plus 2, which would give us the number of hydrogens in a typical alkane. We then subtract the number of hydrogens in the molecule, which is 14. The number of oxygens is not included in the formula, so it will be ignored for the time being. And then we divide that total number by 2, which gives us a degree of unsaturation of 1. And this 1 degree of unsaturation means that there will be a double bond within the molecule. So now, looking at the infrared spectroscopy, we see several peaks on this readout. And so starting at the largest peak down here, if you can see my cursor, we can estimate that this frequency is roughly 2950 centimeters. And the functional group that this frequency represents is a CH stretch in alkanes. And there's also a very pronounced peak at 1750, which would indicate a carbonyl group and is characterized by a carbon and an oxygen held together with a double bond. There's also a peak, just below 1500, let's say 1450, which would indicate an alkane group that's characterized by an HCH bend. And then there's several more peaks clustered together, so we'll just kind of highlight a couple of them at roughly 1250 and 1025, and these two represent a carbon-oxygen stretch. So now looking at the carbon-13 nuclear magnetic resonance data, the first thing we need to do is count the peaks, which give us 6. And this tells us that there's going to be 6 unique carbons within the molecule. Since there are 6 peaks but 7 carbons total, this tells us that 2 of the carbons within the molecule will be equivalent. The highest peak is roughly around 173 parts per million, which would indicate an sp2 carbon that is bound to an oxygen, likely representing either a carbonyl or an ester. As we move further down, here at roughly 60 parts per million, this would indicate an sp3 carbon that is bound to an oxygen, which is likely representing an ester. And then this peak, we can roughly estimate it's around 42 parts per million. This would indicate an sp3 carbon that is adjacent to a carbonyl group. And then the rest of the more concentrated peaks, around 25, 23, and 15 respectively, are all indicative of an sp3 carbon as well. So now looking at the hydrogen or proton nuclear magnetic resonance data, we see that the molecular formula includes 14 total hydrogen atoms. And the graph shows us there are 5 peaks, which means that there are 5 unique types of hydrogens. And by measuring the peaks with a ruler, we were able to obtain data on the peaks. So the 5 peaks measure 9 millimeters, 9 millimeters, 4 millimeters, 12 millimeters, and 24 millimeters respectively. And so what we need to do next is we need to find the hydrogen ratio, and we do that by dividing the length of the peaks by the shortest peak. So essentially what you would do is 9 divided by 4, since 4 millimeters is the shortest peak, you would do 9 millimeters divided by 4, 9 divided by 4, 4 divided by 4, 12 divided by 4, and 24 divided by 4, which would give us a hydrogen ratio of 2 to 2 to 1 to 3 to 6. And so when you add all these up, this equals 14 hydrogens, which means that it matches the number of hydrogens within the molecule. So we're on the right track here. So next, what we need to do is to analyze the chemical shifts. We need to follow the n+1 rule. And this rule states that the number of peaks equals the number of neighboring hydrogens plus 1. So for these, we can we've already done the math in the previous equation for the ratio 2 to 2 to 1 to 3 to 6. For this first 2H, we can count the number of peaks, which 1, 2, 3, 4, which gives us a 4, making it a quartet. And since all these peaks are below 10 parts per million, they will all be in a tetrahedral configuration. So this first peak at 4 parts per million will be a CH2 sp3 carbon bounded to an oxygen with 3 neighboring hydrogens. This next one further down will be a doublet because it only has 1 neighboring hydrogen. And its interpretation is a CH2 with an sp3 carbon and 1 neighboring hydrogen, and it's likely carbonyl adjacent as well. For the next group, this single hydrogen, it's really difficult to estimate how many peaks or neighboring hydrogens there are, but we can roughly guess that it's a non-net. So there's 8 neighboring, so 1H plus 8 equals 9, which would be a non-net. And since it's only 1 hydrogen, it would be just a CH sp3 carbon with 8 neighboring hydrogens. This next one, the 3H one, would be a triplet, and it would be CH3 sp3 with 2 neighboring hydrogens. This peak is pretty far away, so it's safe to assume that it's not part of a carbonyl or an ester group. And then the last peak is the largest peak, which is we previously looked at. It was 6H. And it's difficult to interpret this fully, but it's likely a doublet. And the interpretation of this group is that since these things are so close together, this is the one where it's likely 2 equivalent CH3 groups with 1 neighboring hydrogen. So, by interpreting all the data from the infrared spectroscopy, the carbon-13 nuclear magnetic resonance, and the proton nuclear magnetic resonance, and figuring out, what groups make up this molecule, we can come up with a proposed structure for C7H14O2 based off of the data that we see. And this is what it looks like. So you have 7 carbons, 14 hydrogens, and 2 oxygens, and then you have the 1 single double bond here in the middle.